Right now, legacy AI tokenizers are artificially inflating the computational cost of one of the world's oldest languages by a staggering 2.41 times. Think about that. It is essentially a hidden tax on ancient knowledge, a massive mathematical blind spot sitting right in the middle of our modern artificial intelligence boom.
Welcome back to Learning with Pratik. If you're new here, I try to increase neuroplasticity by exploring a new topic every day. I do all the reading and researching so you don't have to. Today, we're diving into an explainer on a really profound technological paradox. We're looking at a space where cutting-edge, trillion-dollar infrastructure directly collides with a linguistic system that was actually codified millennia ago. We're unlocking what you might call the Sanskrit Code and exposing AI's ancient secret.
Now, to really grasp this paradox, we have to look at how artificial intelligence actually reads. Large language models don't process text the way your brain does. They process tokens. You can think of a token as the fundamental building block of AI data. It's like a discrete mathematical chunk of a word. And this is completely crucial because it's the core metric that dictates absolutely everything in the AI pipeline. It determines the raw compute cost needed to train a multi-billion-dollar model, it dictates the memory bandwidth for massive server farms, and the inference latency, which basically is just how fast the machine can generate an answer for you. But there is a foundational architectural flaw here. Because our current commercial models are trained overwhelmingly on English data, they've developed a severe systemic bias. When non-English users interact with these massive computing systems, they are penalized by this hidden token tax. It quite literally costs them more computational energy, more server space, and more API dollars just to express the exact same human thought.
This bias becomes incredibly obvious when we contrast modern English assumptions with ancient Sanskrit architecture. For example, in English, expressing the thought, "he wishes to go," requires 4 distinct words. That translates to roughly 4 AI tokens. But the Sanskrit equivalent? It's jigamasati, just one single word, maybe 1 or 2 tokens total. And look, this isn't just some weird quirk of translation. Sanskrit utilizes a highly synthetic and agglutinative structure. To put it simply, a single word operates kind of like a tightly packed zip file. It elegantly encodes the subject, the object, the mood, the verb, and the tense all at the exact same time. Information that takes an entire drawn-out sentence in English is compressed with mathematical efficiency into just a few characters. Where English relies on empty spaces and helper words to build meaning, Sanskrit builds meaning from within, stacking prefixes and suffixes into a single, unbreakable semantic unit.
And here's the fascinating part. This extreme information density is absolutely not a historical accident. It's entirely by design. Around the mid-first millennium BCE, a scholar named Maharishi Panini achieved something completely unprecedented. He codified classical Sanskrit. By formulating exactly 4,000 sutras, or generative grammatical rules, in a masterwork known as the Ashtadhyayi, Panini effectively wrote a linguistic algorithm. His system is so phenomenally rigorous that it literally mirrors modern programming languages. By formalizing a deterministic morphology, he created a framework engineered for absolute precision. It's an ancient code that systematically strips away unnecessary alternatives to maximize semantic compression. Panini didn't just write a grammar book, he built a highly optimized data transfer protocol centuries before we even had computers. So this ancient engineering actually builds into a massive, undeniable advantage for modern machine learning. Sanskrit operates on an independent word order, which is driven by its vibhakti system, basically a highly specific set of inflectional case endings. Think about a language like English. Sequence is everything, right? The sentence, Rama killed Ravana, means something vastly different than Ravana killed Rama. The AI relies heavily on where the word sits in the sentence to figure out what the whole thing means. But in Sanskrit, the grammatical role of a word is permanently locked into the word itself through those case endings. You can completely scramble the sequence, and the meaning remains flawless. For an AI, this is a real game changer. It dramatically reduces the model's reliance on rigid positional embeddings. The semantic truth is held securely within the morphology, completely independent of the sequence, allowing the model to process complex logic without wasting computational power mapping out sentence structure.
So you might be wondering, how do our modern, multi-billion-dollar AI architectures handle this ancient efficiency? Well, independent researcher Anshu Kumar actually put this to the test. He conducted a rigorous quantitative analysis using 701 parallel verses of the Bhagavad Gita, and the results completely expose a profound technological blind spot. When evaluated using an unbiased baseline tokenizer, like SentencePiece, Sanskrit requires barely half the tokens of English to convey the exact same data. It is literally twice as compact. But when subjected to commercial production-level tokenizers, the massive engines powering systems like Gemini or OpenAI's legacy GPT models, Sanskrit's natural efficiency is actively destroyed. Rather than recognizing a highly dense, mathematically structured language, the technology actually penalizes it. The modern architecture is just fundamentally mismatched with this ancient compression algorithm.
When we isolate that unbiased baseline, we can truly appreciate the scale of this missed opportunity. An objectively trained tokenizer, one built with an equal vocabulary size and absolutely no overwhelming Western bias, accurately reflects Sanskrit's dense structural design. In these controlled environments, the mean token count for Sanskrit drastically drops below that of English. It practically proves that Panini's centuries-old grammatical rules can successfully outcompress modern English in digital encoding. It is a system built for maximum data transfer with minimal bandwidth. It's a testament to human ingenuity that seamlessly translates into digital supremacy, provided the machine is actually allowed to read it fairly. But the reality inside today's massive data centers tells a very different story. Legacy architectures, like the GPT Clen 100K tokenizer that was utilized until GPT-4, completely fail to parse Sanskrit's compound words and intricate prefixes. Because it lacks the necessary morphological awareness, the AI just arbitrarily shatters these ancient words into tiny, meaningless fragments. This brute force approach forces the character per token density down to a devastating 1.13 that artificially inflates the total token count by 2.41 times compared to English. And that right there is the literal definition of the token tax. It's a massive, hidden, computational and financial penalty forced upon Indic language users, simply because the underlying algorithm is blind to the elegance of their language. When an AI shatters a Sanskrit word, it isn't just wasting processing power. It's driving up the carbon footprint of the server and the monetary cost for the end user, completely wiping out the language's built-in efficiency.
Stepping back for a second, we realize this linguistic precision is exactly what made Sanskrit a true powerhouse in the ancient world. From the early composition of the Vedic Rig Veda around 1500 BCE to Panini's brilliant codification in 500 BCE, the language evolved into a remarkably stable medium. By 300 CE, it ushered in what historians call the Sanskrit cosmopolis. For over 1,000 years, its unambiguous grammar made it the definitive trans-regional link language across South and Southeast Asia. It deeply influenced the formal vocabularies of cultures stretching all the way from Indonesia to Thailand. It was basically the ancient world's premier vehicle for transferring complex, technical ideas across vast distances without losing a single drop of fidelity.
Which brings us to the next vital frontier of artificial intelligence. How do we fix this bias and actively harness this ancient power? Well, the research points to a revolutionary pivot. Instead of relying on probabilistic, English-first models that just kind of guess their way through language, developers must build morphology-aware tokenizers that explicitly integrate Panini's rules. This means teaching AI Sandhi, the ancient deterministic rules for compound splitting, to achieve optimal digital compression. Going even further, the industry could train native Sanskrit foundation models. By pre-training an architecture directly on a large Sanskrit corpus, we could encode vast amounts of human knowledge with a fraction of the parameters. This would drastically lower memory bandwidth, massively reduce server energy consumption, and make artificial intelligence vastly cheaper and more accessible to run globally.
It leaves us with a fascinating, almost mind-bending proposition. We are currently pouring billions of dollars into scaling massive data centers and raw compute power, all while operating on a highly inefficient linguistic framework. The ultimate solution to data compression and semantic density might have already been formalized over 2 millennia ago. It begs the question, could an ancient 3,000-year-old code hold the blueprint for the next generation of artificial intelligence? Let me know your thoughts in the comments below, especially if you have something particular in mind. Thanks for watching. Tomorrow we open a different page. Until then, Pratik, out.